Right. Let's do a little bit of comparison of theories that, I mean, the waves that we have been deriving theoretically now so far, and get into observed waves and the differences. In the second podcast, I see that there is some buzz in the beginning, but during the podcast itself, it seems to have gone away. But if it is a problem, just send me a message. Okay. So this is a table that is looking at the characteristics of observed tropical zonal oscillations and the waves derived from the frictionless drive equatorial wave theory. Everything we did as far as the wave kinematics and the wave interactions and wave characteristics so far was all dry dynamics. We didn't consider any moist processes. So you can imagine that maybe that has something to do with the differences we are looking at here. And here the speed of the background zonal flow is assumed to be minus 5 degrees C, 5 meter per second. So if you look at the stratospheric and tropospheric modes, then you will see that the Kelvin and mixed Rossby gravity waves have periods of 10 to 15 and 4 to 5 days respectively. Wave numbers obviously 1 to 2, 3 to 4. And the phase speeds in the stratosphere 25 to 45 and 25 meter per second. Length scales, wavelength scales. The Kelvin wave has no meridional perturbation velocity, and the mixed Rossby gravity wave has 2 meter per second. And they are pretty close to what we derived from theory. So in the stratosphere, the observed waves with all the moist dynamics, obviously observations have all the moisture dynamics, and the theoretical dry equatorial waves that we derived are essentially the same, almost identical. But when you go into the troposphere, we look at the tropospheric Madden-Julian oscillation, has a period of 40 to 50 days, which is called the intra-seasonal time scale, less than 90 days. We will see later on that this varies from 20 to 100 days, 20 to 60 days, and so on and so forth. The wave number is 1 to 2. We will see that this is quite unique. The phase speed is 4 to 8 meter per second, 4 to 8 meter per second, and a wavelength is 15 to 30 kilometers. Whereas the theoretical wave speed, the Kelvin wave was 15 to 20 meter per second, wavelength was 8 to 9 kilometers, and V was 0, which is similar to the observations of Madden-Julian oscillation. So the phase speeds are tremendously different, about 1/3 or so, right? So this has to be explained. What is it that makes the waves slow down? And if it is convection, then why does convection propagate at all? These are the kind of questions you have to answer. In stationary circulations, the period is infinity, of course. You get wave numbers 1 to 2. It doesn't propagate because it's a stationary circulation. You still have wavelengths of in the vertical of 15 to 30 kilometers. And in theory, the vertical wavelength scale you get out of it is 2 to 3 kilometers with a meridional velocity of 5 meter per second. So it's very critical to understand these differences of in the full moist dynamic system, why do the waves propagate so slowly, and is there only a slow mode, or is there also a wave that propagates as observed? Okay, so let's start with the stratospheric modes. We had our equations before, the zonal, meridional, and the vertical equations. Right? Yeah. So we had looked at the mixed Rossby gravity waves dispersion diagram in terms of the equivalent depth for zonal wave numbers. We had looked at the group velocities and the horizontal and vertical group velocities. Obviously, you remember theoretical mode n equals 0. The dispersion curve and group velocities, we saw that MRG obviously has a eastward group velocity, and the vertical group velocity is downward here, as you can see here, is negative. So we talked about what happens during the long waves and the short waves, and how the group velocity is affected based on the equivalent depth, right? That's the same for Kelvin wave dispersion diagram as well. So you have again eastward group velocity and downward group velocity. For why? Because we were only considering positive wave numbers. Remember, m greater than 0, we had phase speed upward, phase propagation upward, and group velocity downward, right? And the Kelvin waves are non-dispersive, so for any equivalent depth, the zonal wave number dependence was not there. But obviously, as you increase the equivalent depth, you increased the longitudinal group velocity, and as well as the vertical group velocity. Just revise from the podcast because I'm going a little fast on this. We are considering positive wave numbers upward propagating with corresponding wavelength scales. This of course corresponds to transient so stratospheric modes essentially look just like the theoretical modes that we derived as we saw in this table. That's the main point of showing these again. Okay, so the mixed Rossby gravity waves and Kelvin waves in the stratosphere correspond completely to the theoretical modes because the moist dynamics and convection do not affect the wave propagation and wave properties in the stratosphere. Okay, so look at the transient tropospheric modes in the next podcast. I will leave this short. We will just build the case towards adding convection and saying what are the convective processes that we know and how they relate to the wave processes that we have been learning about.